Lesson 21, Refraction and Lenses. The study of lenses is very similar to that of curved mirrors. However, while mirrors involve reflection, in which light bounces off the curved surface, lenses involve refraction, in which light bends as it travels through the curved surface. In fact, for lenses, there are two refractions. One when the light ray enters the lens, and one when the light ray exits the lens. Note that for the convex lens, like the one depicted above, the light ray is bent towards the principal axis twice. While for the concave lens to the right, the ray is bent away from the principal axis. It is for this reason that a convex lens is a converging lens, where light all converges on a single point. Concave lenses are diverging lenses, in which the light rays all bend away from each other and never meet. Part 1. Lens ray diagrams. When you draw a lens diagram, you should always draw a dividing line down the middle vertically. Concave lenses are lenses that dip in on either side. Concave, like a cave. Concave lenses are diverging lenses. This means all light rays that come in parallel to the principal axis refract and diverge away from each other. But if you follow the light rays back behind the lens, they appear to be coming from the same point. This point is a focus, and since this point of intersection doesn't actually exist, we call it a virtual focus. Convex lenses are lenses that bulge out on either side. Convex lenses are converging lenses. This means all light rays that come in parallel to the principal axis refract and converge on a single point. We call this point the focus. It is a real focus because the point of intersection exists and can be measured. Unlike a mirror, each lens has two foci. The primary focus, which is the focus at which the refracted light rays intersect. Concave lenses have a virtual primary focus. Convex lenses have a real primary focus. The secondary focus is a symmetric point on the other side of the lens that is used for drawing ray diagrams. There's some other important lens vocabulary that you should learn before we start drawing ray diagrams. The center for the lens is the center of the sphere that carves out the shape of the lens. The center point is twice as far away from the lens as the focus. It's usually referred to as the 2F point, so you don't get confused with the middle of the lens. Real is the side of the lens that light goes to. This is also the side that the observer looks through. Virtual is the side of the lens that light comes from. A concave lens has a virtual primary focus. A convex lens has a real primary focus. It can be tricky to figure out which focus of the lens is the primary and which is the secondary. How do I remember? If you complete the circle formed by the lens face that the light hits first, the primary focus will be inside that circle. Let's go through a quick summary of everything we've learned so far about curved lenses and mirrors. We'll start with converging lenses and mirrors. Converging lenses and mirrors always have positive foci. This is because the primary focus for a lens and the focus for a converging mirror is always real. It's on the real side. For mirrors, this means you have a concave mirror that dips inward. For lenses, this means you have a convex lens. In either case, they're converging, and the image properties are the same every time. Sur, which means that the image is smaller, inverted, and real. Nur, which means there's no change in size, it's inverted and on the real side. Bur, which means it's bigger, inverted, and real. If it's at the focal point, there's no image produced. And love, the image is larger, upright, and virtual. Next, we're going to look at diverging lenses and mirrors. Diverging lenses and mirrors always have a negative focus. This means that the primary focus, or the focus for the mirror, is virtual and on the virtual side. This is a convex lens or a concave mirror. No matter what, a diverging lens or mirror will have the same kind of image. SUV, smaller, upright, and virtual. We draw ray diagrams to determine the properties of the image when the object is placed at particular places in front of a lens. To draw a ray diagram, you draw 3 different rays. The first ray comes in parallel to the principal axis, and it refracts from or through the primary focus. The next ray comes in through or towards the secondary focus, and it refracts parallel to the principal axis. The third ray comes in through the middle of the lens, and it keeps going in a straight line. Here's an example. First, we need to determine which of the 2 foci is the primary focus. You do this by completing the circle on the face the light reaches first. Inside that circle is the primary focus. The secondary focus is outside the circle. The first ray comes in parallel to the principal axis, and it refracts through the primary focus. The second ray comes through the secondary focus, and it refracts parallel to the principal axis. The third ray goes through the middle of the lens, and it keeps going in a straight line. The image is the location where the 3 rays intersect. For this image, we have SIR. It's smaller, inverted, and it's on the real side of the lens. Here's another example. Again, we first determine the primary focus by continuing the circle on the face of the lens that light hits first. The primary focus is inside this circle, the secondary focus is outside of it. Our first ray comes in parallel to the principal axis. It refracts through the primary focus. The second ray comes from the secondary focus, and because our lens isn't quite tall enough, I'm just going to imagine that dotted vertical line that goes through the lens continues up above it, and it refracts parallel to the principal axis. The third line comes through the middle of the lens, and it keeps on going. We can see on the real side of the lens, the lines will never meet. They're diverging. But if we follow the lines back, we find a point of intersection on the virtual side of the lens. We draw our image at the point of intersection, and we see that our image is LUV, larger, upright, and virtual. Here's our final example. First, we need to determine the location of the primary focus. To do this, we continue the circle on the face of the lens where light hits first. Inside the circle is the primary focus. Outside the circle is the secondary focus. The first ray comes in parallel to the principal axis. It refracts from the primary focus. We draw a dotted line to guide our ray so that it bends at the center point of the lens. The second line comes towards the secondary focus. Again, you can draw a dotted line to help guide your ray to where it bends at the middle of the lens. It refracts parallel to the principal axis. The third line comes to the center of the lens, and it keeps on going straight. Because this is a diverging lens, the rays will always diverge. There is nowhere you can place the object to get a real image. So we have to follow the lines back and find a point of intersection on the virtual side of the lens. We find this intersection point, draw in our image, and find that it's SUV, smaller, upright, and virtual. Part 2, the lens formulas. The same 2 formulas that we used for mirrors will also work for lenses. They are 1 over F equals 1 over DI plus 1 over DO. The second formula is M equals negative DI over DO equals HI over HO. where F is the location of the primary focus from the middle of the lens, positive if it's a convex lens or a converging lens, negative if it's a concave lens or a diverging lens. DO is the distance from the object to the lens. This is always a positive number. DI is the distance to the image. Positive if it's real, negative if it's a virtual image. HO is the height of the object. This is always a positive number. HI is the height of the image. It's positive if it's upright, it's negative if it's inverted. M is the magnification of the image. It's positive if it's upright, it's negative if it's inverted. When you have a magnification equal to 1, there's been no change in size. If magnification is less than 1, the image is smaller. If magnification is greater than 1, the image is bigger. While the equation for curved mirrors and thin lenses are the same, it is important to note that real images form in front of a mirror, and real images form behind a lens. This is due to the fact that mirrors reflect light back, while lenses refract light through to the other side of the lens. Also remember that convex has a negative primary focus, and concave has a positive primary focus. The mirror formulas are best understood through examples. Here's our first example. A 4 centimeter tall object is placed 50 centimeters away from a convex lens that has a focal length of 20 centimeters. Describe the image formed. When solving problems with the mirror equations, it's often best to draw a picture of the situation to help you understand what's going on and visualize it. We start by drawing our convex lens. The convex lens has a focal length of 20 centimeters. The secondary focus is symmetric on the other side. The 2F point is at 40 centimeters. Our object is placed beyond the 40 centimeter point. It's at 50 centimeters, and it's a 4 centimeter tall object. Because of the location of the object, we can estimate that the image will be SIR, smaller, inverted, and real. But let's do the calculations to make sure. The first formula is 1 over F equals 1 over DI plus 1 over DO. We know the focal length of the lens is 20 centimeters, and we know the distance of the object is 50. This means 1 over DI equals 1 over 20 minus 1 over 50. This gives us DI equals 20 to the negative 1 minus 50 to the negative 1, all to the negative 1. This gives us a DI value of 33 centimeters. We should note that this is also positive. Because it's positive, we know that the image must be real. The next formula is the magnification formula. Magnification equals negative DI over DO. This gives us our magnification equal to negative 33 divided by 50. This equals negative 0.67. Because this value is negative, we know that we have an inverted image. Because the magnification is less than 1, we know that we have a smaller image. So our image is smaller, inverted, and real as predicted. Second example. A 5 centimeter tall object is placed 60 centimeters away from a diverging lens that has a focal length of 40 centimeters. Describe the image formed. Again, we'll start by drawing a picture of the situation to help us visualize it. The lens is diverging, which means it's a concave lens. The focal length is 40 centimeters, so we can draw a 40 centimeter mark on either side of the lens to represent the primary and secondary focus. The 2F point is at 80, twice the distance away. The object is placed at 60, and it's a 5 centimeter tall object. We can tell just by the type of lens and the location of the object that the image is going to be SUV, smaller, upright, and virtual. But we go through the calculations to confirm it and to find the exact amounts. The first formula is 1 over F equals 1 over DI plus 1 over DO. We know F is at negative 40. We say negative because it's a diverging lens. The distance of the object is positive 60 because the distance of the object is always positive. This gives us 1 over DI equals 1 over negative 40 minus 1 over 60. This is DI equals negative 40 to the negative 1 minus 60 to the negative 1, all inverted. So we have a distance for the image equal to negative 24 centimeters. The negative tells us that this image must be virtual. Next, we calculate the magnification. Magnification is equal to negative DI over DO. This is negative of negative 24 divided by 60. This gives us a magnification equal to positive 0.4. The positive tells us that our image is upright. The 0.4 is smaller than 1, so we know that it's a smaller image than the actual object. So it's smaller, upright, and virtual. Here's our final example, which will bring your knowledge of mirrors and lenses together. An experiment is done where an optical device, either a mirror or a lens, is used. When an object is placed 20 centimeters from the optical device, so we have DO equals 20 centimeters, an erect image of the object is found. Erect means upright, on the opposite side of the optical device. So let's draw a picture of this. I'll draw a square for our optical device because I don't know whether it's a mirror or a lens. The object is placed 20 centimeters from this optical device, and an image appears upright on the opposite side. The image is 1/4 the size of the object. This means the magnification is equal to 1/4, positive because it's upright. Because the magnification is less than 1, we know that it's a smaller image. The only time a smaller upright image is formed is when you have a smaller upright virtual image from a diverging optical device. In order for this smaller upright image to be on the opposite side, that would mean the opposite side would have to be the virtual side. For a lens, the opposite side of the object is the real side, so this must be a mirror, a diverging mirror, or a convex mirror. But we can do some calculations to confirm this. We'll start with the magnification formula. Magnification is equal to negative DI over DO. So 1 over 4 equals negative DI over 20. This gives us DI equal to negative 5 centimeters. The negative tells us that it's a virtual image. Next, we'll find out the focal length. 1 over F equals 1 over DI plus 1 over DO. So F equals DI, which is negative 5 to the negative 1, plus DO, which is 20 to the negative 1, all to the power of negative 1, which gives us a focal length equal to negative 6.7 centimeters. The negative tells us it's a diverging mirror. And since it's a diverging mirror, we know it must be convex.